Hello guys, so I'm here to discuss another problem from University Physics 14th edition. So we will be talking about problem 26.2. A machine part has a resistor X protruding from an opening in the side. This resistor is connected to three other resistors as shown in figure 26.2. An ohmmeter connected across A and B reads 2.0 ohms. What is the resistance of X? So from the given, let us consider the next. R1 is 15 ohms, R2 is 5 ohms, and R3 is 10 ohms. So the ohmmeter reads 2.00 ohms. So we want to calculate the resistance X. The resistance that measured by the ohmmeter represents the equivalent resistance of the total resistors because these four resistors are connected in parallel. So therefore, we can use equation 26.2, which represents the connection of resistors in parallel. So that will be the reciprocal of the equivalent resistance is equal to the sum of the reciprocals of the individual resistances. So to get the resistance of X, we have 1 over the equivalent resistance minus each resistances. So now we can plug our values for R1, R2, R3, and the equivalent resistance into this equation to get Rx. So we get 2 over 15 ohms. By taking the reciprocal, the value of X is 7.5 ohms. Hi there again. So we are here for another problem to be solved from University Physics. We will have problem 26.3. A resistor with R1 equals 25 ohms is connected to a battery that has a negligible internal resistance and internal energy is dissipated by R1 at a rate of 36.0 watts. If a second resistor with 15.0 ohms is connected in series with R1, what is the total rate at which electrical energy is dissipated by the two resistors? So the figure shows the situation where R1 equals 25 ohms and R2 is 15 ohms. The dissipated power by R1 is 36 watts. We want to find the dissipated power by the two resistors. The battery has zero internal resistance. This means that the voltage drop in R1 is the same as the voltage of the battery. So we can use R1 to get the voltage of the battery before connecting R2, where the dissipated power P1 is related to the voltage by equation in the form P1 equals V squared over R1. So to get V, that will be the square root of P1 times R1. Now, let us plug our values for P1, R1 into the equation to find the voltage across the battery. Then we get V equals 30.0 volts. So this voltage is equal to the voltage in the first and the second resistor. This voltage is the EMF of the battery. After connecting R2, the voltage drop in the battery is due to the equivalent resistance of R1 and R2, which are in series, and its combination is given in the form the equivalent resistance is equal to R1 plus R2. And the total power is equal to V squared over the equivalent resistance. Now we can use this equation to find the total dissipated power by the two resistors in the form PT, or the total power, equals V squared over R1 plus R2. Now we can plug our values for V, R1, and R2 into this equation to get the total dissipated power. We get 22.5 watts. So the total dissipated power by the two resistors is 22.5 watts. Hi everyone, we're here again to solve another problem from University Physics. So today we will be talking about problem 26.4. A 42 ohm resistor and a 20 ohm resistor are connected in parallel, and the combination is connected across a 240 volt DC line. What is the resistance of the parallel combination? What is the total current through the parallel combination? What is the current through each resistor? So in this problem, we are given R1, which is 42 ohms, and R2, which is 20 ohms. They are in parallel, and the voltage across the combination is 240 volts. We are required to find the equivalent resistance, the total current, and the current on each resistor. So we want to find the equivalent resistance of R1 and R2. The two resistors are in parallel, and to calculate their combination, we will use equation 26.3 in this form. So we can plug our values for R1 and R2. We get 31 over 420 ohms. Then we get its reciprocal. So the equivalent resistance in the circuit is 13.55, approximately equal to 14 ohms. To find the current in a parallel combination, the potential difference V across each resistor connected in the parallel is same for every resistor and equals the potential difference across the combination. And we can use the value of the voltage to find the current across the combination by using Ohm's law. We have IT equals total voltage over equivalent resistance. We can plug our values for V and R into the equation to find the total current. Then our total current is 17.71 or 18 amperes. In letter C, we want to find the current in each resistor. So the result in part B represents the total current in the resistors, where total current through resistors connected in parallel is the same for the currents through the individual resistors, R1 and R2. As we discussed in part B, the voltage is the same and V1 equals V2 equals 240 volts. So now we let us use Ohm's law to get the current in each resistor as I1 equals VT over R1. Then plug the values. The current in the first resistor is 5.71 or 5.7 amperes. And for the second resistor, we have I2 equals V2 over R2. Then we plug in the values. The current in the second resistor we get is 12 amperes. So the least resistance allows a higher current of. First, to check the current in parallel, is equal to the sum of the individual currents. So our total current is equal to 17.71 amperes. I1 is 5.71 amperes and I2 is 12 amperes. So add them together, we get 17.71 amperes.